Now we talk about universal functions or UFUNC in NumPy. And these are basically functions or operators that have been overloaded in NumPy. So they are functions that you are familiar with, like plus, minus, times. These are operations that we've talked about, but within the context of primitive data types. So an integer plus another integer, an integer multiplied by another integer. This is division. This is floor division. So you divide and then you take the floor, meaning you round down. Modulus operator, right, to find the remainder. Power operator. So you're all familiar with these, but we've talked about them only within the context of scalar values, meaning variables that contain only one value. Well, in NumPy, which is able to work on matrices of vectors, these operators are overloaded such that they can perform, say, element-wise operations. So you can multiply an array by another array, and it's doing element-wise multiplication. So it's grabbing the first element in array 1 and multiplying that with the first element in array 2, and so on. So that's why they're called universal functions, because they are vectorized wrapper functions. These are examples of some trigonometric functions, exponential functions, which are all universal functions, meaning you can use np.sign on an array or a matrix and so on. So you can do the same for all these functions. Okay, let's see some examples. NumPy.linear spacing, go from 0 to np.pi. So this is the end. So now you see we only have 2 arguments. Before we had talked about 3, right, which will be start, end, and stride. Sorry, in within the context of linear spacing, it's start, end, and then number of points, right? But here you only provide start and end. So how does it figure out the number of points? It uses some default, which is 50. So it uses some default value and gets you 50 numbers starting from 0 and ending in pi, which is roughly 22 over 7, which is 3.14. So we can print the linear spacing, and then you have this list. Vector times equals to, what does that do? This will be equivalent to xvec equals xvec times 2. We talked about this shortened way, which is more efficient. So it's equivalent once again to xvec equals xvec times 2. So it just multiplies every item in the xvec array by 2. So an element-wise multiplication of every item in xvec by 2. And then you can print it. Here we're actually printing the shape. So what do you expect the shape to be? It's just one row, right? Or one column. And then the shape is 50, meaning it created 50 items between 0 and 3.14 inclusive. So you can run it and you get the results on the screen. Like I said, sign from the NumPy package is a universal function, meaning it can act on an entire array, which could be multi-dimensional. Here is just one-dimensional. And then you have yvec, which will be a vector just like x, but each entry in the vector is the sign of these values here, going from 0 to pi. And you can print it. This is what it looks like as the sign of each item going from 0 to pi radians, all right? And you can import matplotlib.pyplot as plt, and then you can do plt.plot, and you provide first the data you want on the x-axis, which of course is 0 through pi, which is stored in xvec, and y is the sine function. And then you can use a red color, solid line, square markers, and then plot.show. And what do you expect to see? A sine function going from 0 to pi. Good. Can run it once more. Oh, because I know pi in radians is what? So if you want to convert pi in radians to degrees, what do you think pi in radians is? Well, maybe an easier way to remember is that 2 pi radians is 360 degrees. And 360 degrees is what will get you the full curve like you have here. So we declared pi. We used pi in xvec, right? And that technically means it will stop about 3.14 here. So I was wondering, why does it give you the full curve? And then I recalled what we did right here. So this is the point where we multiplied every item going from 0 to pi by 2. So invariably, it now goes from 0 to 2 pi, which will give you the full 360 degrees. That's why this curve goes all the way from 0 to 2 times pi. And 2 times pi is 2 times 3.14, which is 6.28, thereabouts. That's why it covers the full range, and then you have the function plot. We also have aggregate functions in NumPy, and they basically summarize data in arrays. So by summary, examples includes minimum, or maybe better still, the mean. So you can have 1 million data set and you want to know the average of all of those values. The mean will act on the entire array and get you one value, which summarizes the data. You can also have values like standard deviation, functions like standard deviation, which gives you the measure of deviation from the mean. It's important to realize that if you're going to be operating on arrays, you want to use NumPy's functions. Why? Because they are much faster than the inbuilt Python functions. So matrix algebra, scientific computation, you're better off using NumPy functions, even if you have functions that will achieve the same purpose built into the standard Python library. And they all have similar function call style. So it's NumPy, np dot whatever aggregation function you want. So minimum, maximum, sum, product, like you can expect. Median, we'll find the median. Percentile, we'll find the percentile, standard deviation, mean, variance, and so on. These argmin, argmax will give you the index where the maximum and the minimum could be found respectively. Very important to understand this axis because it's going to explain the next couple cells that we're going to be talking about. So remember, rows always come before columns, right? If you say you have a 3x2 matrix, it means you have a matrix that has 3 rows and 2 columns, 3x2. The first item is for the row. So you go down the rows first. So that's how I remember these axis 0, axis 1, axis 2. So 0 means you're going down the row because the row is the most important, is the most dominant. So you go down the rows first when your axis equals 0. When axis equals 1, then you go down along the column. And then if it's 3-dimensional, you go the third direction, which is inwards into the screen as shown here. And those will describe the direction in which you want to perform the aggregation functions, as we will see shortly. So we talked about a range, right? And we always had three values: start, stop, and stride or increment. Well, here we have only one argument, and it's 6. What does that mean? It means that value is the stop. So what does it use for the start and for the increment? Well, it's going to assume you're starting from 0. So it assumes you start from 0 because you didn't provide a start, you only provided a stop. You didn't provide an increment, so it assumes the increment will be 1. So it starts at 0 and stops 1 short of 6, which is 5. So what you get from np.arange is 0, 1, 2, 3, 4, 5, and that's it. And then in Python, we typically do this. The results from np.arange can also be operated upon by just using a dot function, and then you do something else on that. And the results from that, you can also do another operation on it, and you can keep having dots, and it will evaluate from the left to right. So the evaluation will be from left to right. So np.arange gets you 0 through 5 inclusive, and then you reshape 0 through 5 such that it has -1 rows and 3 columns. What does -1 row mean? Well, you only need 1 dimension, so I'll explain that here. But it's important to realize that the -1 tells Python to figure it out. So what we have right now is 0, 1, 2, 3, 4, all the way to 5. And those are 6 numbers, right? Because this is 1, 2, 3, 4, 5, 6. 6 numbers. You want to reshape it so that you have 3 columns, is what we said. So how many ways can you reshape this into 3 columns? If you have 3 columns and there are 6 numbers, then there's going to have to be only 2 rows, right? So the number of rows is implied given the number of columns. So you've specified number of columns as 3, then there are 6 numbers. So there's going to have to be 2 rows. So you could have done reshape and then do 2, 3. But the point is only one of these 2 is needed. So if you do -1, 3, Python will figure it out that this -1 means there will be only 2 rows. If you had done 2 rows and then -1, well, only one way to have 2 rows, right? You have 2 rows, then there will have to be 3 columns. So all these arguments are optional. They will give you exactly the same result here. And then we can run it and test that out real quick. So you run it, it reshaped 0 through 5 to be having 3 columns, which is 0, 3, that's column 1, column 2, 1, 4, column 3, 2, 5, right? So we change it to 2, 3. No, it's not just moving on time. And then we run it, no difference, right? We change this to -1, asking Python to figure it out. Figure out how many columns I need, since I already told you what the number of rows will be. It works still. No difference. Good. And like I said, this is Pythonic. You'll get this. This gives you an array 0 through 6. The array I wrote out here. Right, you get this. And then that result, you can operate on it within the same line, which is why we said Python is concise. We use this dot operator, and then it uses the reshape function, which is defined on arrays. And then it reshapes it into this. You can continue, right, and then do sum. Which you will see here. And we'll talk about that shortly. So it will sum up all the elements in the array. So basically, this is a Pythonic code. It's powerful, it's concise. You can continue to stream multiple functions, one after the other, and it's going to evaluate from left to right. Good. So we'll move on. A.size will get you the number of items in that array, which is 6. Ndim will tell you the number of dimensions which will be what? 2, right? There's rows and there's columns. So it's a 2-dimensional array. We can use the sum function, like I said. You can do it this way and say np.sum and you provide a. You can say a.sum. And now we begin to introduce second argument, which is axis. And I already told you, go in the direction of the rows first, right? Rows always come before columns. So this is the direction of axis equals 0. This is the direction of axis equals 1. So here you're asking for axis equals 0, which is downwards. So you're summing this guy downwards. So 0 plus 3 will give you 1. Sorry, 0 plus 3 will give you 3. 1 plus 4 will give you 5. 2 plus 5 will give you 7. So you have 3 values. And it will precisely be 3, 5, 7, which is what this is. If you use the standard, if you use just this sum function, is this from NumPy? No, this is standard Python sum function, right? Because there is no name of package with a dot before it. So this gives you the same results as our numpy.sum with axis equals 0. But we prefer to use which one? This or this? This one. Why? Because NumPy is faster. So with all these matrix algebra calculations, you want to use NumPy. This will give you same result as summing along axis equals 0, which means you're summing downwards. But you could also sum with axis equals 1. That means you're summing sideways from the left to right. So you will take 0, add it to 1, add it to 2, and you get 3. You add 3 to 4, which is 7 to 5, which is 12. So the result will be 2 items, meaning being 3 and 12. That's what you get on the third line. By the way, this is NumPy sum function, not Python's sum function. So if you use numpy.sum and you don't provide this second argument, what do? You sum up all the items in the array, which is 0 through 5, which will be 3 plus 3, 6 plus 9. 6 plus 9 is what? 15. You get only one value when you use NumPy sum function. If you use Python's inbuilt sum function, is equivalent to summing along axis equals 0, meaning downwards. And all of this seems very easy because I've only provided a small matrix. It becomes very important when both dimensions could be 1 million or 5 billion, right? So that's why it's important to use NumPy in those cases, because it will be a lot more efficient than standard Python. There is this option, which is a function in NumPy, which is to set the print options to a precision of your choice. So I can choose to have only 2 decimal places. That's what precision equals to does. How do you generate random numbers in Python? We use NumPy. And this selected portion does the job. It will give you 6 random numbers. And the numbers will be between 0 and 1. And then, like we talked about before, you can reshape it. And you can reshape it such that those 6 numbers will now be in an array with 2 rows, 3 columns. What if we don't want the random number to be between 0 and 1? Then we use mathematics, basically. So I want random numbers. I want 6 random numbers between 10 and 60. How do I achieve that? This is precisely what this does. So to scale the interval, you multiply by the range you want. So the maximum is 1, right? The maximum from this is 1, and the minimum is 0. So you can multiply every item in these 6 element array by 50. So now the number goes between 0 and 50. after multiplying each item by 50. So if you want it to go from 10 to 60, then you add 10 to every item in the array. So the one that was 0 now becomes 10. The maximum, which was 1 originally at this level, got multiplied by 50, it became 50, and then you add 10 to it still, and it becomes 60. So that's how you scale stuff from 0 to 1. I can illustrate it more clearly here. So random numbers between 0 and 1. You want to widen the interval to whatever, say 30. So to widen it to 30, you will multiply this random number. Let me call it n rand. This n rand, you can make it n rand times 30. So that the interval which was between 0 and 1 is now between 0 and 30, right? And then if you want it to be between 20 and 50, then you will take this number that goes from 0 to 30 and then add it to 20. And then the one that was 0 before becomes 20. The one that was 30 after scaling will become 50. So that's how you can generate random numbers over any interval. And it's important you realize and understand this because you will be tested on this. So it's important to be able to generate any random numbers within any interval you want. But you already know NumPy is random.random. Important you remember how to call this. If you just use one random function, it doesn't get you there. You need numpy.random.random and then the number of items you want. You can ask for 100, you get 100 random numbers. Each one goes from 0 to 1. And then you can scale it laterally, so it covers a wider range by multiplying by a constant value. You can move the starting point and the ending point by adding. That's what we've done here. And I'll finish up the rest in the next video. Wow.